This is Unit 3C. It deals with force, mass, acceleration and stopping distances. So starting at the bottom, we can see the concept of velocity, which we talked about in the previous video, is made up of distance per time, and then also we need to know the direction of that movement. And if we combine that with time again, we get acceleration, so how quickly the velocity is changing. And we described it and we graphed it, but we didn't say what actually influences it. And these are two things over here: force, more acceleration, and mass is on the bottom, which means the more mass we have, the less acceleration we have. So mass is a property of matter, and force in this case usually comes from an engine. And we can see it illustrated here. So here we have quite a small truck with a huge load, so small force from the engine, large mass in the back, overloaded, and that will leave us with a small acceleration. By contrast, this is an aerial atom, a very, very fast accelerating car, and we can see that they've stripped as much mass out of it as possible, and they've also put a very forceful engine in it, an engine that creates a great deal of force. So larger force than the top, smaller mass, and a much greater acceleration. We can see the same idea over here in the context of football. So we've got a very, very powerful kicking force, a less powerful kicking force, a low mass modern ball, and then a very high mass old-fashioned ball. And the best case scenario is large force, small mass, and this will really be accelerated very quickly while it's in contact with the boot. In contrast, more mass, it's going to accelerate more slowly, and here we have the situation where we'll get a medium acceleration, and here's the worst case scenario: very large mass and a very small force. Now if we apply this idea to braking, we have basically the same setup. The only difference here is it's a minus force, and what we mean by that is it opposes the motion, so it's a braking force, and that will give us also a negative acceleration, and by that we mean slowing down. But the physics is the same. The greater the force, the greater the slowing down. The greater the mass, the harder it will be to slow down. And over here we should also remember that if we double speed, it actually quadruples kinetic energy, and that's what braking has to wear down, if you like, the kinetic energy. So if we double the speed, we quadruple the kinetic energy. We also quadruple the braking distance. So braking distance over here is the distance a car travels while it's braking. We also have thinking distance, which is the distance you travel between seeing a problem like a fallen tree and actually hitting the brakes. And together they make stopping distance. So there are three factors: the driver, the car, and the road. And the car is split into three, you can see here, and they variously influence thinking distance and braking distance. So be careful, make sure you're answering the right question when the examiner asks. Now we can see that only speed influences both. So if you're going quickly, you'll have a bigger thinking distance and a bigger braking distance. The condition of the driver, so if he's tired or he's been drinking, will influence thinking distance but not braking distance. We assume that the person hits the brake equally hard. Speed, as we've said, influences both. The mass of the car, the quality of the car, by which we mean the quality of the brakes and the tires, will have an effect on thinking distance. Sorry, won't have an effect on thinking distance, will have an effect on braking distance. And finally, the road, by which we mean is it icy, is it slippery, and so on, will not influence thinking distance, but it will influence braking distance. Now here we've got a ideal scenario and a nightmare scenario. So here we've got a slow moving car. It's a very modern car, very big brakes, and the person is sober, so they react very quickly, don't travel very far, and brake very quickly and smoothly there as well. In contrast, this car is overloaded, so the mass is high, going much quicker. Let's imagine he's also drunk, and the brakes are much worse. Now we can see that on the graph here. There's three features of the graph which you can see. The speed is higher, and it takes longer to react, and also, more subtly, the downwards gradient is less here and steeper there.